In this video, we're going to build on our understanding of spanning trees, and in particular, a application or an application of spanning trees where we come up with a network that links all the vertices together, but with the minimum cost. Okay, and I think this is best done by example. Okay, so what we're going to do is let's have a look at this example here. And what we're going to do is we're going to link all 6 vertices together in such a way that it's a tree. A tree uses the minimum number of edges. Okay, so in other words, if we've got 6 vertices, we need to pick 5 edges. If you remember that rule from the last video, okay, so if you have 6 vertices, there's 1 less edge, okay, and that'll form a tree. And also remember the definition of a tree. A tree is the minimum, basically the minimum number of edges needed to link all the vertices, okay, in such a way that there are no cycles, multiple edges, all that kind of thing, right? So it's just a simple network with the absolute bare minimum of edges to link the whole thing together. So we could think of these vertices A, B, C, D, E, F. We could think of them as towns, okay, or cities, whatever, and we can think of the edges as roads. Now, what we see here is clearly not a tree. It's a tangled mess, probably one way to describe it. Cycles everywhere. I don't know if there's any multiple edges in this one. Maybe not. I don't think there's any multiple edges here, but there's most certainly lots of cycles. Okay, that's not a tree. We need to basically extract from this diagram 5 edges. Okay, 6 vertices, we need to pick 5 edges of minimum weight. Let's pretend these numbers, okay, for example, if they're roads, let's say we're building roads, okay, between these cities or these towns, and the numbers indicate the cost of the road, for example, in, say, millions of dollars. We want the cheapest road network with the minimum number of roads needed to link all 6 of these towns together. And we're going to use an algorithm here called Kruskal's algorithm. Kruskal's algorithm is actually probably one of the most straightforward ones. All we need to do is pick the edges or start choosing the edges that are of minimum weight. And then you start to go to the edges of higher and higher weights until you end up with the tree. Okay, and that's it, and then you stop. So what we're going to do first is we're going to, I'm just going to draw the solution just here on the side. So I'm just going to basically redraw the vertices. Okay, so there's A, B, okay, so try to keep it somewhat to scale, or at least put the vertices roughly where corresponding with the original diagram. I think F was somewhere here, okay, and C was somewhere in the middle. Okay, let's start. Let's have a look at the edges in the original diagram, which identify the edge of absolute smallest weight first. Okay, so looking around, you can do this by inspection. You can see that edge CE has a weight of 1. Okay, so, and there's no other 1s anywhere. So when you find the edge of minimum weight, see if there's any others that are the same. So there could be other 1s there as well. In fact, you'll notice that when you go to the 2s, there's 2 of them. In fact, yeah, there's 2. I thought there might have been 3. No, there's 2 there. So let's draw in CE first, okay? Right, so now we've linked town C to town E, okay? Okay. So we've connected 2 of the towns together. Let's go to the next weight up. So there's no more 1s. We've got roads of cost of 2 or weight 2. We've got BD, that's a 2. So let's connect that up. Now, by the way, I could have chosen CF, and I may just do so next, in fact. I'm just going to put the weights there. So that's 1, that was weight 2. Notice, though, that by connecting B and D together, and then C and E together, that what I've done is I've formed a part tree, really. There's 2 paths, clearly, but it's an unconnected or a disconnected network. It's not a spanning tree. It's a tree, but it's not a spanning one. Okay, it basically Kruskal's algorithm just picks edges randomly as long as the edges are of minimum weight. That's the only condition. Okay, so BD's there, C is there. Okay, now we've got FC. Okay, sometimes what I do is I could put a dot or something there to say that I've used that edge up. Okay, so let's use the next edge, which is FC. Now, the other thing as well, that as you're picking these edges, you must not form any cycles. That's a no-no. Okay, no. As soon as there's a cycle, basically it's all over. It is not a tree, it is incorrect. Okay, so be very, very careful that, for example, you don't pick, for example, FE. Oh, there's a number missing on that. And I might just put maybe a 3 there. Just to make it interesting. You'll see why shortly. You cannot choose any edges that then form a cycle, okay, because that's not a tree. All right, so we've used that two there. Now, the next edge or set of edges that we can pick, one up from that, we've got 3s. So we've got a 3 there and a 3 there. Now, FE, okay, can you choose that? If I was to put FE there, let's say I might just draw it apart there. Is that permitted? Yes or no? And hopefully you've said no, it's not permitted. Why is that? Because you've got a cycle. And once you have a cycle, it is no longer a tree. It's a spanning network, but not a spanning tree. You know, it's got to be a tree. Trees are the absolute minimum, okay, of an absolute minimum network that links all the vertices together. Remember that. So this one we cannot pick. Okay, we can't pick that one. That's gone. However, there is another 3 that we can choose. We can choose AB. That's okay, because that doesn't form a cycle, okay, or a closed path. And that's worth 3. Okay, we have quite an interesting network here now. So what we've got 4 edges, and it's a disconnected network, but we've got towns A, B, and D linked together, F, C, and E linked together. Now, if this was an actual road network, let's say this, that we had people building these roads, as they're building the roads, it's like they're building 2 sections and they're disconnected from each other. So during construction, there's still no way to get from A to C, for example. Okay, so it's like there's 2 trees slowly sort of coming together, and eventually they'll link up and it'll form one big tree. Okay, that's how Kruskal's algorithm works. It's kind of just, I wouldn't say haphazard, but you're kind of just picking edges all over the place, and of minimum weight. So now we've used that one there, so that's good. Any other 3s that you can see? No, that's good. No 3s. Okay, 4s. How many 4s do we have? Okay, we've got this 4 here, and there's no other, so we can choose that one there. And what do you think? We stop? I think so. I think we can stop there. First of all, 6 vertices, we have 5 edges. We also have a tree, okay? And we can get from any vertex to any vertex that we want, okay? There's a path between any 2 vertices. We have formed a tree. We have formed a spanning tree. In other words, it is a connected network. Now, what's the weight of this network? Alright, we add up all the numbers together. Oop, and I forgot to put in AF, so that's, sorry, that was a 4. That was the last thing I did. Right, let's add these numbers together. Okay, 1 plus 2 is 3, 3 plus 4 is 7, 7 plus 3, 10, 10 plus 2, 12. Okay, so I'm just going to add them all together, all the edges together. 1 plus 2 plus 4 plus 3 plus 2, which equals 12. And that is the weight of this spanning tree, of the minimum spanning tree. Okay, so next video, we're going to look at another algorithm that produces a minimum spanning tree, so the tree of minimum cost, but it uses a slightly different method. Okay, so, and it's called Prim's algorithm, and I'll be doing a video on that next.